This is the second presentation in Unit 4. It's called Round and Around We Go. We have our famous quote by Archimedes. It was his last words before being speared by a Roman soldier, and uh, it said, "Do not disturb my circles." So, the learning goals are that students will be able to describe speed, velocity, and acceleration and force in circular motion, that you'll be able to calculate tangential velocity, centripetal acceleration, and centripetal force, that you'll be able to relate circular motion to previous learning in kinematics and dynamics. So, what we already know that the velocity can change in magnitude or direction. So I can say I can speed up from 8 to 10 and I can change velocity, or I can change direction and maintain my same number, but whenever I change direction, I'm changing velocity because velocity is a vector. We know that the circumference of a circle can be calculated as 2 pi r, and that's from geometry. Okay? So whenever you know these things right here, you know that circumference is a measurement of distance. So if you were to calculate right here what your displacement is as you go around the circle, remember displacement is how far you are from where you started. And in that case, it would be 0 because you end up in the exact same place. So we know that circumference is a measurement of distance, so really we're talking about speed at this point. So what do we learn in the lab? We learned that circular motion is an extension of projectile motion. We said, okay, if a projectile goes this way and it falls, eventually it'll get to the point where it keeps falling around the Earth, and you get to the idea where you have something that moves in a circular motion or a circular orbit around the Earth. We also learned that increasing the suspended mass increases the velocity. Okay, so the more mass you put here, the faster this thing goes around in a circle up top. We also know that the radius and period determine the velocity. So, what if a bird was shot fast enough that the curve of the Earth actually mattered? And you actually see this. If you actually shoot it fast enough where the projectile moves so fast that it doesn't account for the curvature of the Earth, an object will achieve circular motion around the Earth. That is essentially what happens with satellites. Is you fire them fast enough with a rocket so that they achieve circular motion around the Earth, and you have what's called uniform circular motion, which if you have a satellite a certain way, it's actually called a geosynchronous orbit, where it stays in the same place relative to Earth. So the stable orbit is achieved by just the right speed. If you shoot it too slow, it will never achieve that circular motion. It'll just strike the Earth. Okay, if you shoot it too fast, it'll go this way and it'll just leave the gravitational pull of the Earth. So you have to have a just right speed in order to maintain a stable orbit. So let's look at velocity. Objects are always changing direction as they're moving in a circle. So because of that, when we think of velocity, velocity includes magnitude and direction. So because of that, we can say that the velocity is always changing even when the object stays at something like 10 meters per second, because the direction is always changing. We also know that the velocity moves tangent to the circular path. So if you look anywhere along the circular motion, anywhere at this point, you can predict the velocity as a tangent line. Now remember, a tangent line is a line in which only one point touches the circle. So this right here would not be a tangent line because it would hit the line, it would hit the circle there, and it would hit the circle here. So that doesn't reference a tangent line. A tangent line is one that only barely touches it. Now, objects moving in circular motion at constant speed are still accelerating, and the reason why is they're always changing direction. So since the object is always changing velocity, it must always be accelerating. So let's look. It says developing A1. Draw the velocity vector of an object moving counterclockwise. So the object is moving counterclockwise, which means it's moving this way. If the object is at the rightmost path on this rightmost point on the circular path. Here's the rightmost point on the circular path. You can't get any further right than that point right there. Now the velocity vector is always tangent to the circular path. So I know it's going to be a line like this, where it only touches at one particular point. Now the last thing that I need to do is I need to put the arrow. And the arrow can either point up or down, but if you realize that it's moving counterclockwise, then it has to be moving in this direction. So we would call that the tangential velocity. Next it says, what is the velocity of a circular saw? 0.4 meters in diameter that completes 200 rotations every second. So the first thing that you need to look at is we need to say, okay, this right here is really not even a calculation so much as a conversion. So if it does 200 rotations per 1 second, Then the next thing we need to realize is, okay, what is one rotation and how does it link to meters? Realize that whenever you go once around with the saw, what you've really done is you've used the circumference. So the circumference is what's going to go there. So all I have to do is calculate the circumference and it will go in this particular box. Remember, the circumference is 2 pi r. I was given the diameter. So in other words, you can say it's pi d, or 0.4 pi. When you plug 0.4 pi here, you'd have 200 times 0.4 pi, and whenever you multiply that out, it ends up being approximately 251 meters per second. The next one we have is also a proficient level question. It says the Earth travels in circular motion about the Sun as shown below. How fast is the Earth moving in standard units if the Earth travels a distance of 1.5 times 10 to the 11th meters, completing 3.15570 seconds? So really what this means to say is that's the distance to the Sun. So the distance to the Sun is 1.5 times 10 to the 11th. So what we need to do at that point is we need to be able to calculate the total circumference of the path of the Earth. Velocity is going to equal to our displacement divided by time, where our displacement in this case is actually going to be a distance, is going to be the circumference, which is going to be 2 pi r over t. Now this t I drew as a capital T because that represents the period of one rotation, or one revolution in this case. So that's how long it takes to go around once. So now I would say 2 pi, and then my radius is really large, it's 1.5 times 10 to the 11th, divided by 3.1557000, which is the number of seconds in 1 year. When you take this and divide it out, you actually get the velocity of the Earth to be a pretty high number. It ends up being about 29,900 meters per second, which is pretty fast. You're talking about the idea of something on the order of almost 300 football fields per second. It's pretty big, pretty fast. This is moving through space. Next, it says an athlete participating in the hammer throw can rotate the hammer at 10 meters per second. What is the period of rotation if the hammer has a chain length of 1.8 and the athlete has arms of 1.1? So realize the radius of the path right here not only includes the length of the chain, but has to include the length of the arms as well. So when you do this, you have to realize that the radius is not in fact 1.8 or 1.1, but instead 2.9. Once you've done that and you know the velocity, you can say velocity is equal to 2 pi r divided by the period, or in our case it would be 10 equals 2 pi 2.9 divided by t. We would multiply both sides by t, divide both sides by 10, and when we do that we end up getting a period of rotation of about 1.82 seconds, which is pretty slow for the hammer throw. So now we need to explore the idea of changing velocity again. Remember that anytime you have a change in velocity, it always has to be due to some sort of acceleration. Now, we know that this acceleration has to be directed towards the center of the circular path, and we can do this kind of geometrically. If you were to kind of draw a tangent line here, which is the velocity at one point, and draw the velocity vector here, which is the tangent at another point, you can actually take these two vectors and you can put them together like this, and that what you see is the connecting arrow represents the change in velocity. Well, whenever you do that for any of the arrows that are along this circular path, especially the ones that are extremely close together, what you'd realize is that the arrow connecting these two is always pointed towards the center of the circular path. So what we do is we call this acceleration centripetal. In other words, it's called the center-seeking acceleration. So the acceleration for an object moving in a circular path is always directed towards the middle point of the circular path, and we call the centripetal acceleration a sub c. So centripetal acceleration can be calculated. It's a little bit different in its calculation as opposed to velocity. Velocity was basically the same. You take how far it went divided by time. Now the centripetal acceleration is a little bit different. It's this idea of the velocity squared divided by the radius. So we're going to introduce this. We're going to say centripetal acceleration is AC, and it's the rate of change in velocity, just like all accelerations are, that's pointed to the center in circular motion. We know that vt is tangential velocity, so that's how far it travels, um, the rate of change in position as it travels in a circle. And then finally, you have the radius. So if we were to look at this is an athlete throws a discus rotating at 3 meters per second and an acceleration of 8 meters per second squared. What is the length of the athlete's arm? So in this case, we know we're using the equation AC equals vt squared over r. That's our equation for centripetal acceleration. We know that the acceleration is 8. We know that the velocity is 3 squared, and we divide it by r. Multiply both sides by r, and when you do that, you get 8r equals 9. Divide both sides by 8, and when you do that, you end up getting the radius, which is approximately 1.125 meters. In a proficient level question, it says, what is the acceleration of a tetherball when it's at its maximum distance from the pole of 2.1 meters while moving at 12 meters per second? Okay, so now we take a look at it and we say, okay, centripetal acceleration is equal to velocity squared divided by the radius. In this case, I know that the velocity is 12, which I'm going to square, divided by 2.1, which is going to be the radius. And when I do that, I end up getting a value of about 69 meters per second squared. Now that right there in and of itself would not be a proficient level question. That's still a developing level question. But the second part says, in tetherball, the length of the rope is constantly changing. How does the acceleration change when the length of the rope changes? Now this is kind of an interesting question because there's more to it than just simply saying, oh, the radius goes down, therefore the acceleration goes up. That would be the case if velocity didn't depend on radius as well. Remember, you have an equation for velocity that is 2 pi r over t. That term is squared. So you have to take things like this into consideration. When I take that and divide it by r, yes, I'm going to have r on the bottom here, but I'm also going to have r squared on the top. So actually, when you reduce the radius, you're going to somewhat decrease the acceleration, which is somewhat counterintuitive. So you need to be aware of those sorts of things whenever you're looking at a problem. So you say, okay, yes, radius is on the bottom, but does this depend on radius? And it does. The mastery level question says a CD has a diameter of 120 millimeters. We're going to have to do something with that, and rotates at 480 rotations per second. What is the acceleration of a point on the edge of the CD? So now we would say, okay, 480 rotations per second, and we would say one rotation is 2 pi r, which we need our r value for. So we would plug in our r value, which would be 0.12 meters. And the reason why it's 0.12 meters, you'd say 120 millimeters. There are 1,000 millimeters in 1 meter. It equals 0.12. Alright, so now when we multiply this thing across, we would get our value for our velocity. And once we have our velocity, which is 361.7 meters per second, we also have our radius, which is still that 0.120. We can now plug in and we can solve for the centripetal acceleration of a CD. We would use the equation AC equals VT squared over R, or we would say 361.7 squared divided by 0.120, which is going to be a rather large number. Okay, whenever we put it into our calculator, we would say 361.7, just one second, we would say 361.7 times 361.7, and then we would end up dividing it by 0.12, and when you do that, you get an exceptionally large centripetal acceleration of 1.09 times 10 to the 6th meters per second squared. Now we need to talk about the idea that we have an acceleration, and all accelerations are a result of a net force. So in this case, we have an acceleration that we've titled the centripetal acceleration. Now that acceleration has to come from a force. Now, what you need to realize is that centripetal force is not a force like gravity or friction. It's not a force that's occurring in nature. Instead, what the centripetal force is, it's a description of the net force. So it's saying that whatever you have, the net force is equal to the centripetal force. And the only reason the net force would equal the centripetal force is if the object is moving in a circle. Okay, so you need to realize that it's not going to be like, oh, why is it moving in a circle? The centripetal force. It would be gravity has a net force resulting in a total force that we can describe as the centripetal force. The centripetal force just means it's moving towards the center, but it has to come from something else. Now it says an object below is moving counterclockwise, circular motion. Draw the velocity, acceleration, and force vectors at point A. So here's point A. The first thing I need to do is I need to draw a tangent line, and that represents my velocity. Now I need to follow the rules that I have as far as the object's moving counterclockwise. So I would draw here, and that would represent the tangential velocity. Now from that point, the object is moving in circular motion, so you would say that the acceleration is directed towards the center. And because of Newton's second law, the force and the acceleration are always in the same direction. So you would additionally say that the centripetal force is in the same direction as the acceleration. Now, what force is required to keep a 10 kilogram object moving in a circle with an acceleration of 2 meters per second squared? Even though the object's moving in a circle, you still have your same basic idea of F equals ma. You're given your acceleration, you're given your mass. You would just plug in and you would say 10 times 2, which should equal 20 newtons. Now, this is just saying the acceleration is centripetal in this case. I don't need to do any other calculations except F equals ma. Now, the last example is going to be a little bit more difficult. It says, what is the centripetal force required to keep Earth in orbit around the Sun if the Earth completes one revolution per year at an average orbital distance of 1.5 times 10 to the 11th. So what we want to do is we eventually want to solve for the force. In this case, it's going to be the centripetal force. In order to do that, I need to know the mass and the centripetal acceleration. Now I do have the mass, but I don't have the centripetal acceleration. So when you don't have the centripetal acceleration, what you can do is you can plug in the equation for centripetal acceleration in there. And so I could take this and I can plug it in there and I could get Fc is equal to mvt squared over r. Now at this point, you could actually enter this information because we actually calculated these things out already in an earlier example. If you didn't know what it was, you could solve for the velocity and then you could plug it in, or you could enter it in algebraically as well. You could say, okay, Fc is equal to m, and then v, remember, is 2 pi r over t squared divided by r. Or a more simplified version of this would actually be, I don't know if it's simplified or not, but you'd say Fc is equal to m, and then you'd have 4 pi squared, and then you would have r divided by t. What that did is we had r squared originally, but I had another r to cancel it out with, and then the t should be squared as well. So once you have this particular equation, you could just enter in your numbers. You would say, okay, my mass is 5.98 times 10 to the 24th. I could multiply that by 4 pi, and the pi is squared. And then I could multiply that by the radius, which is 1.5 times 10 to the 11th. Divide that whole thing by 31,557,000 seconds. And we did that conversion earlier in this presentation, or you could know that 1 year is 365 days, which is 24 hours, or excuse me, 1 year is 365 days, which is 24 hours, and in each hour there's 3,600 seconds. When you take this thing and you take this whole big thing and you divide it out, you end up getting the force that's required to hold the Earth around the Sun, and it ends up being a number of about 3.56 times 10 to the 22nd newtons. Now when you do this, realize once again that this centripetal force is not a force in and of itself. It's a description of other forces that's saying, hey, this thing is making it move in a circle. Now you're probably familiar with the reason why the Earth goes around the Sun as gravity. But we are going to explore the concept of gravity in the next presentation.